remind you that these are
have regular and irregular polygon with sides and or angles, ranges and sizes, although they must still be straight and joined up. Some triangles, quadrilateral, sides, pentagons, 5 sides, hexagons, 6 sides, heptagons, 7 sides, nonagons, 9 sides, and decagons, 10 sides. Some extra facts about polygons that you may need to remember are: a regular quadrilateral has a special name. It is called a square. There are different types of triangles. An equilateral triangle is a regular triangle, and a right-angle triangle and an isosceles triangle are examples of irregular triangles or irregular polygons. It is important to remember that all the internal angles of a regular polygon are equal.
So let's go through those now.
The size of each of the interior angle of a regular polygon equals n take away 2 times 180 degrees divided by n, where n is the number of sides. So, for example, a regular pentagon has 5 sides. Using the formula above, 5 minus 2 equals 3. 3 times 180 degrees equals 540. 540 divided by the 5 sides equals 180 degrees. I hope you enjoyed learning all about polygons. If you have any questions, please comment below. We would like you to subscribe, and don't forget that we've just released a new Alexa skill. Just search High Five Maths or check the description for the link.
The major sixth and the minor sixth. And as you may have guessed, these intervals once again have simple relationships to the initial note. So we now have all of the intervals that are generally considered consonant. The remaining intervals included in the 12-tone Western system are considered to be dissonant, but this doesn't mean that they're not useful. Although dissonance in music seems like something you want to avoid, music without any dissonance at all may sound pleasant, but will lack any drama or suspense and won't have a sense of tension and release. So let's add the traditionally more dissonant intervals. These are the tone, or major second, the minor seventh, the tritone, the major seventh, and the semitone, or minor second. So these are the 12 intervals available to us in the Western 12-tone system. But why can't we just add a couple extra pitches in between a few of these? For example, a neutral third, which would be between the major and minor third. Or we could have a note between the major seventh and the octave, creating a sort of octa-seventh or octa-leading tone. The thing is though, we can't really just add these 2 extra microtone winkles and leave it at that. This is because it's quite important that the notes between the octave are more or less equally spaced. This allows us to easily play in different keys, and generally makes the instrument much easier to play. With the standard 12 pitches in the octave, the notes are naturally spaced at fairly equal distances from each other. But if we add just a couple microtonal notes in like this, it will destroy that equal spacing. If we're going to add more notes beyond the standard 12, we will need to find an alternative way to evenly divide up the octave, which can still allow us to play all of the most important intervals, like the perfect fifth, the perfect fourth, etc. 19 notes in the octave is a fairly good alternative. 19 evenly spaced notes in the octave still allows us to play our most important intervals, like the perfect fifth, the perfect fourth, etc., whilst also allowing us to access a whole range of other microtonal notes. Another option is to have 24 notes in the octave, adding a new microtonal note between each of our standard 12 pitches. This of course maintains all of our standard intervals, whilst adding a whole range of new microtonal notes. Some musicians have written music using systems like these. Ivan Wisniewski, for example, developed a quarter-tone piano, which features 24 notes per octave. But as you can see, having access to these extra notes makes the instrument significantly more confusing to play. Even though 19 notes per octave, or 24 notes per octave, allow us to play a whole range of additional microtonal intervals, I think most musicians would agree that these extra microtonal notes are not useful enough to warrant reducing the playability of our instruments. Of course, some instruments like the violin or the trombone don't have to be modified to access the notes between the standard 12, but instruments like these are still built to optimize 12 notes in an octave. The instrument's design, size and shape are all dictated by making sure the instrument can comfortably access 12 notes in the octave. The design of a musical instrument has to strike a compromise between being comfortable and practical to play and having access to as many notes as possible. And it turns out that over the centuries, we've come to this conclusion that 12 notes in an octave, repeating up and down the keyboard, is the best solution to this problem. 12 notes in an octave is the best way to access the most consonant and useful musical intervals, whilst also optimizing the playability of our instrument.
Lomba cuci piring anti-bakteri. Sabun cuci ekonomis lawan Lifebuoy pencuci piring.
Optimizing the playability of our instruments. So that's it, right? We found our 12 notes. So we can now just double each of those frequencies to give us another set an octave up, and we can half them to get another set an octave down. And if we do that a couple more times, we wind up with the full span of a modern piano. Job's a good one, right? Well, not quite. There is one more topic left to discuss. Temperament. See, right now, we've tuned our instrument to what's called just intonation. Our intervals are tuned to perfect ratios, which is ultimately the purest way to tune an interval. But even though this is the purest way to tune our intervals, it presents a problem. Do you remember when I mentioned earlier that our notes need to be evenly spaced if we're going to be able to play in different keys? Well, even though the 12 notes of just intonation are fairly equally distanced from each other, they are not perfectly evenly spaced. This is because each interval was tuned using a different ratio away from the root. For example, the fifth between the A and the E is a perfect 3-to-2 relationship. And this does mean if we play some music in the key of A major, it's going to sound really pure and perfect. However, if I try playing in a different key, E flat major for example, things are not going to sound quite as harmonious. The problem here is even though this perfect fifth between the A and the E was a perfect 3-to-2 relationship, the perfect fifth between the E flat and the B flat is not. When you change the key, you're effectively changing the root. So unless you're going to retune your instrument relative to that new root every time you change key, other keys are going to just sound out of tune. This is really limiting, right? We want our instrument to be able to sound good in any key, not to mention being able to play chromatically outside of the key. So how can we fix this? Well, with something called temperament. If we want to be able to play in various keys on one instrument and play chromatic music that goes outside of the key, we're going to have to adjust or temper some of these intervals. The way in which you adjust these intervals to make the tuning more versatile is called temperament. And across history, various temperaments have been used, which each find their own way of striking a compromise between preserving how these intervals should sound and being able to play in different keys and tonalities. The system that we use today, which has almost been universally adopted, is called 12-tone equal temperament. 12-tone equal temperament makes sure that every note is the exact same distance from every other note. So in equal temperament, a perfect fifth between A and E will sound just as in tune as a perfect fifth between B flat and F, or D and A, or E and B. The way this is achieved is, instead of tuning every interval as a perfect ratio, we just tune the octave as a pure ideal ratio, and then we divide the space between each octave into 12 equally spaced notes. This division does a pretty amazing job of approximating these intervals. But of course, apart from the octave, the intervals in 12-tone equal tempered music are no longer exactly perfect ratios, and therefore slightly out of tune. Some equal tempered intervals are only slightly different from their pure intonation counterparts. For example, the perfect fifth and the perfect fourth are only 1.96 cent away from their ideal tuning. However, some of these intervals are quite significantly sharper or flatter. An equal tempered major third, for example, is over 13 cents sharper than it would be in pure intonation. You can hear this difference most distinctly in chords. If I play a C major chord in our usual 12-tone equal temperament, you'll hear a wah 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 sound, because the three pitches of the chord are not perfectly in tune with each other. This wah wah sound is called beating. However, if I tune the C major chords to just intonation, this beating sound disappears. The thing is though, like I mentioned, almost every piece of music you've ever listened to is in 12-tone equal temperament. So although these intervals are slightly out of tune, they're just in tune enough that we don't really perceive any sort of difference when we listen to our music. So hopefully this video has at least in part answered the question of why Western music generally uses just 12 notes. For such a simple sounding question, the answer can actually be quite confusing, being a tangle of history, physics, and human preference. And of course, you don't have to stick to just 12 notes. Microtonality, for example, is music that uses notes beyond and between the 12 standard pitches. And many non-Western cultures around the world use completely different tuning systems. I'm actually planning a future video on how different cultures around the world approach tuning and pitch, so if you're trained in a non-Western style of music, I'd love to hear from you. Also, a big thanks goes to Modart, who gifted me a copy of their Pianotech software to help me make this video. Pianotech is a super versatile piano plugin that lets you tune your keyboard to any possible tuning. So I thought it would be fitting to wrap this video up with this piano piece that I composed in just intonation. And as always, a massive thank you goes to everybody who supports me on Patreon, including Adam Granger, Andre Santiago, Andrew Brown, Andy Deacon, Austin Barrett, Austin Russell, Bob McKinstry, Brittany Parker, Bruce Mount, Cameron Oliveira, Chris Cabell, Christopher Ryan, Kieran Bennon, Darren Harvey, D. David Lee Fish, David Fundifer, Dr. Darren Wicks, Eleanor Skorchenko, Esben Hansen, Eugene Leroy, Eyes, FD Hodor, Gilna Modatona, James Kao, Jay Kuckensparger, Joe Watson, Jonas Soderstrom, Justin Bigger, Lavender Monrose, Meg Fellows, Melody Composer Squared, Michael Vivian, Nancy Gillard, Paul Miller, Paul Hazel, Peter Dunphy, Roger Clay, Sam Lynn, Steve Daly, Thomas Armstrong, Tim Beaker, Tim Payne, Toot, Vidal Flowers, and Vladimir Kodakov.